and I'll be giving today's lecture on settlement and consolidation. So I understand that we have a couple of latecomers that are still sort of signing in. So what I'll do is I'll just give them 2 or 3 minutes just to get in and signed in. But for now, for those of you who are signed in, if you can hear me clearly, just please raise your hand using the icon on the GoToMeeting input menu. And if you're having any troubles with the audio, just type into the chat box, and I'll do my best to adjust it for you. So once again, we'll be starting in just a minute now. Okay, perfect. So it looks like everyone's here. So yeah, let's begin. Okay, so all of our material is copyrighted, and also keep in mind that you'll all be receiving a copy of the materials at the conclusion of the session. So I know I haven't sent out all the materials for session 4, so you can look out for actually a combination of session 4 and session 5's materials by the end of this week. Okay, so as far as today's learning objectives, so these are the main sort of 3 things that we'd like everyone to get out of these courses. So first, we want everyone to understand just the fundamental principles of settlement and consolidation, then the theoretical principles associated with 1D consolidation analysis, specifically the lab test, which we'll go into, and then also how to utilize numerical modeling programs for 1D consolidation analysis. Okay, so I just see into the chat box here. Okay, so someone's having a little bit of an issue with the audio. So excuse me, everyone. Let me just make a quick adjustment, and then I'll get back to you. Okay, perfect. So, okay, So the audio is fixed. Everyone can hear me now? Perfect. So now let's continue. So today's presentation, for those of you who are coming in late, it's 1D consolidation and settlement. And here is just the background of what we'll be going over today. So first, this session is divided into 4 different sections. First, we'll be going over background information. There's principles of consolidation as well as lab testing, result analysis. We'll go over how to interpret the results that you get from your testing or your lab testing. And then third, during the third chapter, we'll go over drainage, which is sort of remediations that are used to increase the speed of draining. And then last, we'll go over a quick numerical modeling demonstration. I'll show you how you can use our program called SoilWorks to model a sort of a drainage and settlement type project. Okay, so first, part 1. So some of the main things to remember about consolidation. So consolidation is the process by which soils decrease in volume under long-term static loads. So essentially what you'll have is a project site or a specimen, and it'll have it'll consist of water as well as naturally soil particles. So obviously this is sort of an exploded view. Naturally your soil particles will be much smaller, as well as sort of the spaces that hold the water. And then as weight is applied upon the soil, water will slowly begin to be pressed out incrementally. And then ultimately you'll have sort of a final settlement stage when all the water is pressed out, and then the strength of the overall soil has been increased. So in general, just sort of in a general term, it is a process by which reduction in volume takes place by the expulsion of water under very long-term static load. So if you're working in a very sort of clay-filled area that's saturated, and you build any sort of structure upon it, you can expect a certain degree of consolidation. Now, this consolidation can take several weeks, or can also take sort of several years, which we'll go into later, which is something that tends to complicate sort of design projects that are built in these areas. So for projects that are built in very clay areas is something that you really need to take into account, and you really need to study before you can commit to any sort of final design. So ultimately, settlement occurs when stress is applied to a soil that causes soil particles to pack together more tightly, and ultimately it reduces its bulk volume. So another good way to sort of understand how settlement works is using this spring analogy here. So as you can see in this particular diagram, you'll have a spring with some water that's sort of encased in water here, and there's a valve keeping the water from coming out. Now, this is, before you sort of, this is, sort of the initial stage, actually. So let's, when you just build your structure. So actually, when most clay soils that are saturated, when you first place your structure and your load upon the soil, it actually won't settle right away. There'll be some quick, immediate settlement, but the really long-term consolidation is actually something that can take, like I said, an extended period of time. And then in the second stage here, this is when consolidation occurs. So, eventually that valve comes loose. And then, little by little, the water gets expulsed out of this encasing here. Or in the case of soils, the water drains to the surface. So as you can see, as this load, continues to stay there, it's slowly going to settle until finally the water is displaced completely, and the soil has all the load. So that's an important thing to keep in mind, is how the sort of the water and the soil both sort of play a part and how settlement and consolidation occurs. So just keep in mind that at the beginning, your soil is saturated. Then over time, that water is drained out from the soil until ultimately you have your final consolidation, your final sort of settlement. Okay, so an important thing to remember is that there's a very distinct difference between compaction and consolidation. So compaction, which I'm sure you're all familiar with, is actually applicable to all soils. It's a very instantaneous process. So just imagine, like a specimen of sand or a specimen of dirt. If you apply a sort of immediate force on it, naturally there's going to be some instantaneous or some immediate settlement. But there's a very big distinction between compaction and consolidation. So the main difference here is that consolidation is a time-dependent process which is only applicable to clay soils, and it can occur over many years. So that's the first difference to take into account, that compaction is immediate, it's instantaneous, whereas consolidation, it's a very time-dependent process. It takes much longer, that can be drawn out. The next thing to keep in mind is that compaction is applicable to unsaturated soils. So as you can imagine, instead of water filling the air voids, there's just air. So that's why compaction is so much faster, because there's no initial resistance. There's just air. Whereas consolidation is applicable to saturated soils. So there's a decrease of water in the air voids, and then naturally there's air voids compact. So that's another key principle to remember, is that it's really the water, the fact that the clay is saturated, that makes consolidation take so long. It's because it takes so long for that water to be pressed out of those pores. And another important thing to remember is how clay soils have very sort of small, tiny pores that take a very long time for water to be squeezed out of. That's what makes sort of clay a very sort of difficult or a more complex material to work with. Another important thing to remember is that the dry density of compaction increases and the water content doesn't change. So water doesn't really play any sort of part in compaction. Whereas in consolidation, as dry density increases, water content decreases as well. So that's sort of the main thing to remember about the differences between compaction and consolidation. First and foremost, that compaction is instantaneous and it's immediate, whereas consolidation, it's drawn out over several years. Compaction, water doesn't play a role, whereas consolidation, water is very key. It's a very important role. Okay, so now let's discuss sort of types of settlement. So as you can see here to the left, we have a uniform settlement, which is actually the ideal kind of settlement that you would want. This is a sort of settlement that, as an engineer or as someone doing a design, that you would want to go for, that you'd want to predict for your site. So as you can see, the settlement is uniform across the entire length of the project. So the structure settles uniformly. So there's any sort of structural issues. Everything stays level. But then you also have two other types of settlement called tipping and differential settlement that lead to complications. So tipping settlement, well, actually let's go to differential settlement first. So differential settlement is when obviously there's more settlement occurring on one side of the structure than the other, and it often leads to cracks in the structure, or especially in the foundation, which is very problematic. And it's something that, if it's predicted that's going to happen, is something that needs to be remedied before you can actually build a structure. So you need to account for differential settlement. Whereas tipping settlement, this is sort of an in-between between uniform and differential settlement. So as you can see, there's still the settlement is still not uniform. It's still not level, but it isn't as drastic. So with tipping settlement, this could be something for that you might be able to get away with for certain structures, even though you'd still want to avoid it. Whereas differential settlement is something you definitely have to remedy. If you can predict, or if you simulate a certain amount of differential settlement in your project site, then in most cases you'll have to find some way to remedy that. And it's usually done through drainage, which I'll discuss in the third chapter. Okay, so now as far as settlement occurs, or excuse me, as far as settlement is concerned, what you want to do as an engineer and when you're doing your designs is to calculate what's called the total settlement. In order to do that, you have to find these three values here. First, you have to find your immediate settlement. So this is when your project or your structure is first put into place. It's almost like compaction, whereas it's sort of immediate. You sort of see immediately sort of a certain amount of settlement, which is very easy to calculate. But it's these two here, primary and secondary consolidation, that require much more work and much more time and effort. So primary consolidation is the drainage of water from voids allowing compression of the soil skeleton. So over a certain period of time, usually a couple of weeks, sometimes a couple of years, you'll have primary consolidation in which the water is slowly being pushed out of the clay. That's something you need to account for, because you want to see, or you want to predict how deep your structure and how quickly your structure will be settling over X number of weeks or years. And then after primary consolidation, you have something called secondary compression, which, as it says here, is a creep, movement, plastic adjustment of soil fabric under a constant effective stress. So this is essentially, once all the water is drained out, there's still going to be a certain amount of compression or settlement due to the fact that your soil or the plastic properties of your soil are sort of compressing. They're being more broken down. So typically, secondary compression is much less drastic than primary consolidation. It's something that it's settlement that still occurs, but it's much less. It's much smaller in magnitude. Let's put it that way. So really, primary consolidation is where most of your settlement will occur. And what we'll do is we'll take a look at this graph here. And this is just sort of a graph that sort of shows how settlement occurs over time for typical projects. So as you can see here, this first phase here, 1 week to several years, or excuse me, sort of hard to see here, but this line that's going straight down here represents your immediate settlement. So this is something that you can predict, right away, just based on your soil properties and your loading. But then after that, as you can see, settlement gradually sort of goes down here, and it sort of reaches this area called primary consolidation, or reaches this sort of range called primary consolidation, where the foundation will, sort of gradually and over time settle as the water drains out of it. And then eventually, and as far as how long it lasts, it really depends on several factors. It depends on the number of static, or the amount of static load you're placing upon your soil, as well as the clay properties themselves. But typically, it can take several years for full consolidation to occur. After which you have secondary compression, which, as I said, doesn't really have much to do with the drainage of water, but it has more to do with just your soil compressing over time due to the constant static loads. So as you can see, once your project reaches secondary compression, the settlement really sort of starts to level off here. So even though it's secondary compression is still something you need to account for, it's typically primary consolidation that's like your main focus, just because it has the most amount of settlement in the shortest amount of time. Okay, so another important thing to remember about consolidation are the physical characteristics, or the physical differences between sand and soil. Some important things to remember is that sand doesn't consolidate. But typically what will happen is you'll be working in project sites where the bottom or the lower layers consist of clay and the top layers consist of sand. So you need to make sure, or you need to understand sort of how the characteristics of each soil type differ and how that will affect your analysis. So the first thing to remember about sand is that the permeability of sand is very high, so water drains in and out of it very quickly, whereas the permeability of clay is very low. So this is directly related to the size of the pore size of clays and sands. So sands have very large pore sizes. That's why drainage happens so fast with them. So if you can imagine, if you've ever been to the beach and you've maybe held like a handful of sand, you put water through it, water will come out through the other side very quickly. Whereas if you have like a large piece of clay and you were to pour water on top, the water would actually just sort of congeal along the top, and it would take maybe even a couple of days before that water actually seeped into the clay itself, let alone seep to the other side. Now imagine that on a much larger scale, having a large sort of clay layer that's saturated and placing a very large structure on it. In order for that water to drain or to be pushed out of that, or out of those tiny clay pores, would take weeks or years. So that sort of ties into the next principle. So drainage occurs immediately with sand. With clay, it's very time delayed. With sand, elastic and consolidation processes cannot be isolated, whereas with clay, settlement can be separated. So there's three sort of distinct stages. There's elastic or immediate settlement, then there's primary consolidation and secondary consolidation, which we'll discuss in further detail. With sand, primary consolidation is incorporated in the elastic parameters, whereas with clay soils undergo consolidation settlement not only under the action of external loads, also known as surcharge loads, but also under its own weight, or the weight of soils that exist above the clay, also known as geostatic loads. So typically, your sand will be your top layer, whereas your clay will be your sort of bottom layer. So you have to take into account multiple loads for clay. And then sand is coarse-grained, and it does not undergo consolidation settlement due to a relatively high hydraulic conductivity. That means it's very permeable. And instead, they undergo immediate settlement. And clay soils undergo settlement when dewatered, also known as ground or water pumping, because the effective stress on the clay increases. So I know that's sort of repetitive with that first point, but it's that's one of the main things to remember just about the differences between clay and soil, is how they behave with water. Okay, so now let's talk about lab tests, and specifically the 1D consolidation test. So the main purpose of a consolidation test is to obtain soil properties which are used in predicting the rate and amount of consolidation settlement of structures founded on clay. So for those of you who took geotechnical courses, you should all be pretty familiar with the 1D consolidation test. So what you'll do is you'll take a clay sample and you'll do a certain test on it, and you'll get certain soil properties or parameters that you can use to predict how that clay will react under a certain amount of loading over a certain period of time. Okay, so its water flows out in any direction. The process itself is three-dimensional. However, the soil is confined laterally, and I'll show you a picture that better illustrates this. So because the soil is confined laterally, or it's supported laterally, vertical one-dimensional consolidation theory is acceptable. So you'll only be worried, or you'll only focus on how that soil deforms in one dimension vertically. And then the permeability of the soil influences consolidation, obviously. When you're working with different sort of types of clays, some clays are more porous or more permeable than others. Naturally, the clays that are less permeable will take a longer time to consolidate and to settle. Okay, so this is just a picture of the eudometer. So as you can see, eudometer tests are designed to simulate the one-dimensional deformation and drainage conditions that soils experience in the field. To simulate these conditions, rigid confining rings are used to prevent lateral displacement. So that's what these rings are over here. So when you put your soil sample in, it'll actually be surrounded by this metal ring that'll support it laterally. So that way, the test is a pure sort of 1D test. So change can only occur in the vertical direction. So porous stones are placed on the top and the bottom of the sample to allow drainage in the vertical direction. So when you have your clay sample, in order to allow drainage or to simulate, field drainage, you'll have these porous stones both on the top and the bottom of the sample. And then to better simulate one-dimensional strain, a diameter to heighten the sample of 3:1 or more is used. So because the process of consolidation involves the movement of water out of soil, it's very important to prevent the drying of the soil. So it's important to keep your soil, make sure that the soil doesn't dry out just naturally. So make sure to keep it out of the sun and to keep it out of areas where it just might evaporate. That's why it's important to sort of close it off like this, so the water just doesn't escape on its own. It has to be pressed out. And naturally, some labs they'll have multiple eudometers running at once, and they'll have it linked up to their computers, just so that they, instead of having to record manually, they can just have everything recorded on the computer. As you can see, this is what sort of a close-up of what your soil sample will look like once it's pressed in there. So these rings, support the sample laterally, and these are the porous stones that allow drainage to occur. So a stiff confining rim with a sharp edge is used to cut the sample of soil directly from a large block of soil. So then excess soil is carefully carved away, so you sort of shape your clay or your soil into that circular disc there. And you'll leave the sample with a diameter to height ratio of usually about 3 or more. Porous stones are then placed on the top of the top and the bottom, once again to provide drainage. And then a rigid loading cap is then placed on top of the upper porous stone. Such as that. And what will happen here is once that cap is put into place, you'll actually load it. You'll actually connect it to this steel rod, which simulates the load increments. And then when you're finally done, the whole, it's all rigged up to this sort of loading frame. Okay, and this is essentially what you'll be studying, is how over time that specimen or that sample will settle as that load is constantly being applied to it. So what you want to get is your sort of a void ratio. So as you can see at the very beginning, this is sort of your ratio of your voids to solid, and over time, as the water is pressed out and the clay or the soil compresses, the voids will close, and you'll have a smaller void to solid ratio. And using this ratio and plotting it against time, you can then get certain factors, or not certain factors, but certain material properties that you can then use to predict settlement and to predict other things about your soil. Okay, so now let's have a quick summary of what we just went over. So consolidation is a process by which soils decrease in volume under long-term static loads. The consolidation process involves a gradual decrease in volume as water in saturated soil is replaced by air. The main differences between consolidation and compaction are as follows. Compaction occurs immediately, while consolidation can take many years. Compaction applies to unsaturated soils, while consolidation applies to saturated soils. Differential and tipping settlement occur when soils settle unevenly under static loading and can cause cracking. So these are things that need to be taken into account, when building or when designing for your structure. And then settlement is a summation of immediate settlement, which happens, right away. Primary consolidation, which occurs when, as water is over time pressed out of your pores and pressed out of the soil. And then secondary compression, once all the water is drained out, that's just plastic deformation of your soil. And then consolidation occurs in clay soils because it takes much longer for water to be forced out of its pores compared to sand and other soils. So that's the main sort of characteristic to keep in mind about clays, is that when it's saturated, the water takes a long time for it to be pressed out, and that's why settlement takes so long. And then eudometers are used to perform one deconsolidation test, whose main purpose is to obtain soil properties which are used in predicting the rate and amount of consolidation and settlement of structures founded on clay. So that's the main lab test that's used to predict consolidation or to simulate consolidation, are eudometers. And what we'll do in the next chapter is we'll show you how to graph your results and then use your results to get certain properties which can then be used to predict or to simulate certain settlements over a certain amount of time. Okay, so now let's have a quick quiz just to review what we went over. So like all the other quizzes, it'll be 3 questions. You'll have a total of 5 minutes. And once we hit the 4-minute mark, I'll make sure to give everyone a warning. So as far as the quiz itself, it's very simple. 5 minutes is plenty of time. But make sure to read each question carefully and read each answer carefully before submitting your answer. And let me pull it up. Okay, perfect. So now Okay, everyone, we're at the 4-minute mark, so for those of you who are still wrapping up, just make sure to complete or to submit your results, or excuse me, submit your answers within the next minute. Okay, everyone, so now let's move on to the next chapter, the next section of our presentation here. Okay, so part 2 will go over, plotting the results of the unidometer test, as well as determining certain material properties, and then we'll go over the empirical equations that are typically used to predict settlement. Okay, so whenever you're doing your unidometer test, the main material properties that you want to determine are as follows. So first you want to get the maximum past pressure. This is the maximum stress that the soil has been subjected to in the past. The compression index, which indicates the compressibility of a normally consolidated soil. The recompression index, also known as the swelling index, which indicates the compressibility of an over-consolidated soil. So as far as normally consolidated soil goes, I'll go over what that means in a minute. And then the coefficient of consolidation, which indicates the rate of compression under a load increment. So these first 3 material properties can be used in empirical formulas to calculate your settlement, whereas a coefficient of consolidation is something that you'd calculate to sort of give an indication of how fast or at what rate, anyway, your settlement will occur. So these are all very important results that you need to get from your unidometer test. They're very important whenever you're simulating any sort of settlement for a particular project site. So now let's discuss sort of what your deformation plot will look like. So once you do your test, your plot should look something like this, and keep in mind that time is in a logarithmic scale. So first, stage 1, you'll have your initial compression. So immediately, there might be some, depending on the sort of soil type you're using. Usually there's some immediate settlement that occurs just because there's sort of pores near the top where the water drains out very quickly. So you'll have some quick initial compression. Then afterwards, you'll have primary consolidation, where excess pore water pressure dissipates and the volume changes over a certain length of time. Once again, as far as unidometer tests, they're usually done for a period of maybe like a couple of weeks. And then secondary consolidation, which occurs after excess pore water pressure due to dissipation. So after the water is drained out, you'll have a certain amount of plastic deformation and readjusting the soil particles. And then once you reach secondary consolidation, as you can see, the settlement sort of levels out. So your main sort of area of interest is this middle section here, primary consolidation, which is once again where the bulk of your settlement will occur over a period of once again that depends. Usually it's like a week or so when you're doing the unidometer test, but it could be even longer if you have like an extended test that you want to run. And then here are your void ratio pressure plots. So this is just something that you can use as a reference. When you have your specimen, it'll have something like this, and this is what your void ratio will look like. And then naturally this will change as settlement occurs. So I won't go over in detail what exactly or these equations. They're pretty self-explanatory. Just keep in mind that what you want to get is your initial void ratio, which you can define by these 3 sort of methods over here. And then what you'll do is you'll take your void ratio pressure plots. So as you can see, you have your change in void ratio due to the first loading. So another thing to keep in mind is sometimes you'll have loading and reloading. For whatever reason, sometimes engineers like to simulate maybe construction loads, or sometimes there's certain areas that will have loads on it and then they'll have those loads taken off. So that's another good way to sort of examine how that compression or how that settlement will occur. So you'll have this sort of a function or this sort of curve based on the results that you get. So it won't be this shape exactly naturally, but the curve should follow this basic pattern. Now we have our void ratio pressure plots. So once again, you have your void ratio E, which you calculated or which you determined, or you determined a series of them anyway for your test, and against your effective pressure, which is on a logarithmic scale. So the main thing to remember from this particular slide are the two definitions of clay based on stress history. So first we have normally consolidated clay. So what this means is that the present overburden pressure, also known as the effective in situ stress, is the most the soil has ever seen. So essentially what's happening is you have like a sample of clay or a sample of soil, and the pressure or the load that you're putting upon it at the present moment is the most load that it's ever been pressed under. Then you also have overconsolidated clay, which means that the present overburden pressure is less than the soil has experienced in the past. So the maximum past pressure, or excuse me, the maximum effective past pressure is called the preconsolidation pressure, or maximum past pressure, which is something that you can determine from your lab tests. So which is why, as you can see here, the curve sort of follows a loop. So this is based on loading and unloading. So there's a certain amount of loading. The clay gets unloaded. And as during this period of time when the clay is unloaded, the void ratio goes back up again. The effective pressure naturally, when it's unloaded, it's going to go down. It's going to go back, and then you reload it again. The reason why we have overconsolidated clay, or why we need to examine overconsolidated clay, is that when clay has been overconsolidated and it's reloaded again, it acts a little bit differently than normally consolidated clay. And that's something we'll go into later on. But just keep in mind that you have to remember, what these two sort of terms mean. So normally consolidated clay means like it's the most it's ever been, it's under the most pressure it's ever been under, whereas overconsolidated clay, it's been under more pressure before. So typically overconsolidated clay, when it's sort of put under less pressure than it's been pressed on before, it won't settle as much, and it'll actually be stronger than normally consolidated clay, just because it's had that pressure placed on it before, so the pores are more compacted. And then how to determine the maximum past pressure. So what you'll do here is you'll have your void ratio versus your effective pressure in a logarithmic scale, and then you'll just follow these steps here. So essentially what you'll do is you'll just find slope that'll correspond to your maximum past pressure. So first, visually identify the point of minimum radius of curvature on a logarithmic scale. So point A here, as you can see, that's your point of minimum radius of curvature. And you can usually do this just by glancing or just by sort of closely looking at your curve. Then draw a horizontal line from point A, so just a horizontal line straight across. And then draw a line AC tangent to point A. So as you can see, there's the tangent. And then draw a line bisecting it, AC, or excuse me, angle BAC, so BAC, so here's D. And then project the straight line portion on the curve to intersect point AD. So this intersection is the maximum past pressure, also known as point F. So right over here, you pull, you just have to sort of, draw your line going down, and there's your maximum past pressure or preconsolidation pressure. Okay, so once you have that pressure, the next thing you do, and keep in mind this is for normally consolidated clay. So first, just to sort of give you a view of what's going on here. So here you have your slope of the field virgin consolidation curve compression index. So it's this line over here. So here, as you can see, is your virgin consolidation line. And then you have your slope of your rebound curve, also known as your swell index. So naturally, when your when your soil is loaded then unloaded, there's going to be a curve that occurs here, sort of a loop. And in order to get your swell index, you just draw this sort of tangent, or you get the slope of this this particular curve here. And then you have your maximum past pressure, which I just discussed how to get, and the initial vertical effective stress, which is right over here. So as you can see, they sort of equal each other. So once you get your maximum past pressure, at this point here, you get your virgin consolidation line, and then you can get your compression index as well once you get that slope. Okay, so now let's go over just a quick sort of sample of how to do this for normally consolidated clay. So as you can see, once you have all of those values, you can get, or you can use this empirical formula to calculate your settlement or your primary consolidation, SP. And as you can see, you just use all of these sort of values and plug them into this equation here. You can get SP. So, once again, in order to get really sort of good at using, analyzing these curves, you just sort of have to practice, drawing the lines and, graphing them yourself. But once you get used to it, it's, fairly straightforward. And usually, what you'll have is an Excel spreadsheet where you can just punch in your values from your tests, and then your primary settlement will be calculated for you via those spreadsheets. So you don't really have to worry about memorizing this equation. These are all just sort of done for you. What really matters is just how to, first how to plot this graph, and then how to interpret it and get these particular results. So really, it all starts with getting your determination of maximum pass pressure using this methodology here. Once you do that, you can get your virgin consolidation line, and you can get your compression index. And then once you find this loop here, or once you have this loop plotted out here, you can get your slope of rebound curve or swell index. And then once you have that, you can just use this to get your primary settlement. Now for over-consolidated clay, the process is a little bit different. So as you can see, you also need to get, for over-consolidated clay anyway, is you need to get this value here, which is your compression index. So as you can see, if you go back here to primary settlement for normally consolidated clay, the equation or the empirical formula is a little shorter. Whereas if you go here, there's a whole other step here. So now I won't go into detail about how this step was derived, but just keep in mind that because if clay has been over-consolidated, there's certain other factors that need to be taken into account. First and foremost, this value here. So as you can see, this value corresponds to your, go down here, to your maximum, or excuse me, your initial vertical effective stress, and then also this value here. So you have sort of two slopes to take into account. But then as you do so, you'll be able to, as you can see, C sub r is used in this particular portion of the equation here. So that's why, over-consolidated clay takes sort of an extra step. But now, there might be some projects where you don't need to, or you don't maybe have the time to really, invest into a odometer test, which is normal. So what we have here are compression indexes, estimates from other laboratory tests. So essentially what you can do is you can, find maybe which category your clay or your soil falls into, and then based on, tests that have been done extensively in the past, you can, get a reasonable prediction of how that soil will behave. And you can get those factors, or you can get your, index here by using these equations. And, just keep in mind that LL equals a liquid limit. So that's something that you'll need to keep in mind. So even though, you can still avoid the odometer test, you'll still have to get your liquid limit through your typical lab tests. So once again, these are the references. For those of you who have, worked extensively with consolidation or settlement before, you should be familiar with these references. I'm sure you've used them in the past for, maybe smaller scale projects or more conventional projects where you didn't need to go to the expedient of doing your own odometer test. And then here's some other compression indexes, some other values, or excuse me, some other references that are available to you. So once again, you'll need to get your liquid limit, and for some of them, you'll need to get your specific gravity as well. But these are all available to you if you don't have really the time or the funding, or you don't really feel the need to do your own odometer test. You can just use these and get very conservative results. Okay, so now let's talk about secondary consolidation. So in order to get secondary consolidation, it's fairly simple. You have your void ratio versus time in a logarithmic scale. And then you would just get, this particular, or use this empirical equation to get your secondary compression index, as you can see. And then using this empirical equation, you get your secondary compression index, plug it into this formula. As you can see, T1 and T2. So this is sort of when your slope starts to level off. That's usually where you'd get those 2 points. And then you get those 2 times, and then you'd import them, or excuse me, you'd plug them into this equation, and then you could get your secondary consolidation. And what you do is you would add this to your primary settlement, and then you'd get your, and you'd add it to your immediate settlement as well, and then you get your total settlement. So fairly straightforward. And as far as the coefficient of consolidation, which is once again that value that sort of gives you an idea of the rate at which your soil will consolidate, there are certain ways that you can get it, but which I'll go into. So there's the logarithm of time method and the square root of time method. But the main things to remember is that it generally decreases as the liquid limit increases. And then it's determined from one deconsolidation test lab versus per load increment. So once again, you'd be able to get your coefficient of consolidation from the odometer test. So as far as the methods are concerned, so the logarithm of time method, I won't go into, just in the interest of time, I won't go into step-by-step details of how to get it. But essentially what you do is you have your deformation versus your time, and then just following these steps here, you'd be able to just sort of get that value just by, analyzing your graph. Okay, so you follow these steps, and then also another important thing to remember is you also have a T sub V value, which you would get from a table. So once again, these are available for reference in most geotechnical resources or textbooks. So you get your value, and then you'd be able to get your value for your coefficient of consolidation. And then for the square root of time method, here you have your deformation, increasing, going down. And this versus the square root of time, and then just using this function or using this sort of method, you'd be able to get your coefficient of consolidation. And also keep in mind once again that you'd still have to refer to a table for your T sub V values. So it'll depend on 90, 80, etc. % consolidation. And sort of depending on the degree of consolidation that you have or the percentage, you'd get the right time, or you get a specific value for time, and then you plug it into this equation, and then you could get your coefficient of consolidation. So really it's a matter of preference as far as which sort of method that you use. Obviously this one's a little simpler. So a lot of engineers, I know they prefer using this one instead. Okay, so now let's go into a quick summary of what we went over. So the 1D consolidation test is used to determine the following soil characteristics: the maximum pass pressure, which is the most pressure that the clay or the soil has been subjected to in the past, the compression index, the recompression index, and then the coefficient of consolidation. The void ratio is determined by recording the settlement of a soil specimen over a period of time. So there are two definitions of clay based on stress history: normally consolidated clay and over-consolidated clay. So once again, just to push the point across, normally consolidated clay is when the clay or the specimen is being subjected to the most pressure it's ever been subjected to before. Whereas over-consolidated clay, usually this applies to reloading. So it's when the specimen or the clay is being placed under less pressure than it's been exposed to in the past. The maximum pass pressure, compression index, and recompression index can be determined by referring to the void ratio versus effective pressure graph. Once again, you get this from your odometer test. And the primary settlement for both normally consolidated and over-consolidated clay can be calculated by using these values in empirical formulas. So once you get these values, you can just plug them into your empirical formulas, and you can get a fairly realistic prediction of what your primary settlement will be. Secondary settlement can be determined by calculating the secondary compression index from the void ratio versus time graph of the 1D consolidation test. So once again, it's another sort of method that's out there that's typically used, where you have your odometer test readings, you have them plotted out, and then just based on your graph, you can get certain functions, or not certain functions, but certain material properties or characteristics that can be plugged into these empirical formulas to predict your secondary settlement. And then the coefficient of consolidation can be determined by either the square root of time method or the logarithm of time method. So once again, these are just two different ways to get the same sort of coefficient. It's just different ways of reading different graphs. So really, it depends on which one that you prefer, and also keep in mind that you still need a sort of a table to refer to for your T sub V values. Okay, so what we'll do now is we'll have our second quiz. It'll be 3 questions, 5 minutes. All multiple choice, and once again I'll make sure to give everyone a heads up once we hit the 4-minute mark. So I'll pull it up now. Good luck everyone, and make sure to just read each question carefully before selecting your answer. Okay, everyone, we're at the 4-minute mark, so just make sure to wrap up and submit your quiz by within the next minute. Okay, so now let's move into part 3. We'll go over drainage, or sort of how consolidation is remediated. So we'll go over usage of drains and then how they're installed. Okay, so let's talk about vertical drains. So as you can see, vertical drains, what they do is they increase the rate of water flow out of the soil. They increase the rate of primary settlement, which is very key. They increase storage capacity of landfills, and they also extract contaminated groundwater. So the main sort of benefits are obviously these two over here, and then these are sort of other benefits as well. But these are the two main ones that are of interest, to engineers. So as you can see, vertical drains, when they're inserted here, what they do is they allow the water to drain out of the area faster, to drain out of your soil faster. So just imagine, without all of these drains, the soil would have to naturally be drained out of the water. Be drained out of the soil, sort of very slowly, just by being compressed through the pores. But now with these drains here, the water now has a much sort of faster path to be extracted or to be drained out of the specimen. So historically, the design of structures, of structures on soft compressible soils or clays, it's created a lot of problems for civil engineers. I discussed just about how the differential settlement can cause a lot of problems, especially. So construction without some sort of soil treatment is usually impractical due to unpredictable long-term settlement. So typically, when engineers enter an area with very saturated clay layers, what they'll do is they'll do drainage just to make sure that the settlement occurs, very quickly. So what they'll do is they'll install these drains, and they'll also apply their own load on it to increase the consolidation, or to increase the settlement. So that way, they can drain all of the water out, all the settlement occurs, and then afterwards, then they'll build their structure, and there'll be a very minimal amount of settlement. So consolidation of soft cohesive soils using prefabricated vertical drains. Also, we'll talk about PVDs, or prefabricated vertical drains, in more detail. But also, there are also sand drains, which are used to sort of drain the soil out as well. So let's talk about sand drains. So sand drains, as you can see, this is sort of how they're installed. So first, what you do is you have an auger that's placed at this drain location. So this particular location is drilled out, it's hollowed out, and then sand is then poured into this tube here as it's taken out. So as the soil is being removed, or as the clay is being removed, it's being replaced with sand. And then it's filled with sand to the top, and then that's your drain for that area. And then it'll be a sort of a long series of drains, or these sand drains, being placed along the project site. So why specifically are they using sand? So the reason they're using sand is because as we discussed in the first chapter, that the permeability of sand is sand is much more permeable than clay. So as you can see, if you can imagine a certain amount of weight being applied to the clay here, naturally the water is going to try to escape. So instead of having to go all the way up to escape and to drain, what it'll do is it'll just flow over here to the side, or to where the sand drain is, and the water will come up naturally through the sand. which will speed up the drainage, as well as consolidation. So this is something that's very useful. It's proven very useful to sort of increase the rate of settlement for increase the rate of settlement and consolidation for clay or saturated clay areas. So because typically what will happen is when you have an area like this, it's not really safe to build a structure on it right away. Instead, what you want to do is you want to drain the area and then build a structure on it. So that way, like I said, settlement and consolidation will be minimized when the structure is actually loaded onto it. But in addition to sand drains, we also have something called prefabricated vertical drains, also known as wick drains. So PVDs, they have what's called a channeled or a studded plastic core, as you can see here, and it's wrapped with geotextile. So the plastic core functions as sort of a support for the filter fabric, and it provides longitudinal flow paths along the drain length. It also provides resistance to longitudinal stretchings as well as buckling of the drain. And the drain jacket itself, so that prefabricated layer there, what it does is it acts as a filter to limit the passage of fine-grained soils into the core area. It also functions to prevent closure of the internal water flow paths under lateral soil pressure. So as you can see, as far as how they're installed, it's a very sort of similar system. You have sort of like an auger, or sort of like a drill that'll empty out these long vertical areas here. But as this drill is working, it'll also insert these drains sort of one by one. And as you can see, as the water is drained out, it's sort of channeled out through these tubes here. So let's get to a better view here of what the installation process looks like. So this is just sort of a side view of the installation process for PVDs. So when they're installed, they'll be surrounded by what's called, or they'll be covered, encased in what's called a mandrel. And essentially what the mandrel does is it minimizes the cross-section area, and it'll reduce the potential for soil displacement and disturbance. It also may be suitable to taper the mandrel tip, as shown here, as long as the stiffness is not sacrificed. So for soils with exaggerated soil layering or large sort of permeability ratios, the layering or the mandrel will enhance the permeability, or the just sort of the way that it's layered will enhance the horizontal permeability. So as you can see, once it's installed here, the mandrel surrounds it, and then it's removed, and then there's this anchor plate that's sort of fitted there at the bottom, which sort of anchors it and keeps it in that final drain position. And now to get an even better view of the installations here. So as you can see here, you have your excavator, and then you also have like a stitcher, and you have what's called a drain row. So instead of so this makes it a lot easier actually for the installation, just because what will happen is in the next step here, as you can see, it's drilled, or it'll the excavator will drill like a long sort of bore hole, or a long sort of vertical shaft here, and then as it does so, it'll insert the drain, and then it'll be surrounded by the mandrel as well. And then what will happen is this part will come up, or the mandrel will come up, and it'll leave the drain behind along with that anchor, and then the drain will be cut in this section here. And this makes it very efficient to sort of go step by step, or to do your spacing. So it can all be done with this excavator, following this very systematic and very straightforward process. And this is sort of what it looks like out in the field. So as you can see, the spacing is done fairly uniformly. Here are all your drains sort of laid out. And then over time, over a certain period of, usually it's a couple of weeks or maybe a couple of months for larger sites, the water will be drained out. And it's applicable to these sort of soil types. So something we'll talk about in the next couple of slides is the sort of limitations of drains and when they can be used. So as far as the applicable soil types, as you can see, they can be used in inorganic silts and clays of low to moderate sensitivity. They can be used in organic layers, decomposed peat, naturally clay and silty sand, so clay materials especially they're going to be used for, dredge spoiled, and then varved cohesive deposits. And we'll talk more about what varves are in a minute. So just keep in mind that when you do your draining, or also keep in mind that when you're doing any sort of consolidation analysis, or you're designing for a consolidation project, typically you'll be involved in analyzing designing the drain spacing, which we'll discuss sort of at the latter end of this chapter. So whenever you have, a large project site that consists of very saturated clay, it's very common to do the design or to do sort of a draining period first before actually building your structure on the site. So let's talk about certain advantages of prefabricated vertical drains. So certain advantages include is that they decrease the amount of surcharge required to achieve the desired amount of pre-compression. So I know I didn't go into this in detail previously. So essentially what surcharge is it's a load that you apply to your project site to get it to sort of compress. So what drains do is they decrease the amount of load required to get your site to settle or to compress as you'd like. And also they're more economic than sand drains. So they're actually in order to make sand drains, you have to get the sand over to the area, and then as far as the process, it also takes a bit longer as well when you're using sand drains. Whereas with prefabricated vertical drains, it's much more economic because you don't have to bring all that sand in. You just have sort of this roll for your drains, and then it's faster and easier to install than sand drains. Once again, just because you don't have to fill up the openings with sand. You can just put that prefab PVD or prefabricated vertical drain there. And as you saw in the previous slide, the stitcher is very effective at just sort of churning that roll out and cutting each drain. So it's actually a very sort of simple and straightforward job as compared to a sand drain, which takes a bit longer and it's a bit more costly. However, there are some disadvantages or rather shortcomings of prefabricated vertical drains. So if the compression layer is overlain by dense fills or sands, very stiff clay or other obstructions, drain installation could or may not, so sorry about the typo though, it could or may not be feasible. So just keep in mind that when it comes to particular dense or very stiff clay layers, then installing these drains might be difficult just because it takes longer for the auger or the drill to get through, or sometimes it can't go through at all. And also, where sensitive soils are present or where stability is concerned, disturbance of the soil due to drain installation may not be tolerable. So just keep in mind that for very dense or for very stiff or for very loose soils, drains may not be feasible, for obvious reasons. If you have very sensitive soil, then, disturbance can happen very quickly, and then, your drains might be inoperable just because, over time, or once the excavator leaves, maybe there might be some displacements that will keep your drain from working. So if in areas where they're particularly sensitive or loose soils, drains may not be, or prefabricated vertical drains anyway, may not be your best option, because they could get clogged if displacement occurs. And then also ground frost due to winter conditions can prevent drain discharge. So typically drainage is done during times of spring or summer where it's not expected for any freezing to occur. It's not done during winter for obvious reasons. If your water freezes, you're not going to be able to drain your area. So that's another thing to keep in mind, is to make sure to plan out your draining time during a time that coincides with warm weather. Okay, so another thing we need to talk about is varves, or RVARVs. So what varves are, they're annual layers of sediment and sedimentary rock, as you can see here. So here you have a layer of sediment, sedimentary rock, sediment, and sedimentary rock. So this happens sort of seasonally with certain certain layers of soil. So the classic varve archetype is sort of like this light and dark colored couplet, and it's deposited in this particular example in a glacial lake. So the light layer usually comprises of a coarser silt or fine sand deposited under high energy conditions when meltwater introduces sediment load into the lake water. So if you have maybe an area or a project site that used to be located near a lake, or that maybe used to be located near sort of like a pond or a water-filled surface, and this is a very sort of natural effect. And the reason I'm talking about this is just because it'll affect the effectiveness of your drains. So if you're working in areas with a lot of varves or this type of layering, what will happen is it'll sort of slow down, or it'll impede your prefabricated drains and you might need to increase the number of drains. And I'll talk about this more in greater detail. So as far as prefabricated vertical drains, there's three sort of project categories that you need to look out for. Project category A is when the soil is basically uniform, so there's no varving, there's no layering, and there's low to moderate sensitivity, which means the soil is fairly firm, fairly stiff, so you won't have to worry about it displacing and clogging up your drains. And then simple construction, so you don't expect any sort of stage loading for your project. So when this is the case, category A, PVDs are fewer in number. And here's sort of your typical length. Here you have your intermediate level, which is something that it'll be sort of a mix between, as far as how your drains are spaced. So it'll be a mix between these two. So let's go to the other extreme, which is project category C, which is used for unusual soil. So if you have lots of varves or high sensitivity, it's not impossible to drain these areas. It just takes more effort. Also, if you have stage loading or complex construction, this is something that will also lead to more effort on your part in order to do the drainage properly. What will happen is this will actually increase the number of drains that'll be necessary. And as you can see, the length is greater than that specified in project category A. And once again, if you have something intermediate, then naturally you're going to have like an intermediate sort of solution. But these A and C are sort of the main ones to look out for. So if you're working in this sort of project site, once again, I'll just reiterate, if you have basically uniform soil with no varving or no layering, you can expect to use sort of a fewer number of PVDs, and then this will affect your spacing as well, which I'll get to during the last section of this chapter. Whereas if you're working in soils with lots of varves and high sensitivity, complex construction, then you're going to need more drains, longer drains as well, and then spacing will be a little closer together as well. And let's talk about this in greater detail here. So something you'll need to account for is the coefficient of consolidation for your horizontal drainage, and then also your coefficient of permeability for horizontal seepage, which we'll discuss here. So for category A, projects may use the horizontal drainage conservatively, and you can estimate it just by this sort of ratio over here. So C sub V, which you calculated from your eudometer test, and then you multiply it by this ratio, which is usually taken to be 1 just as a default value. So that's what you can use for your horizontal drainage. So these are estimates, but field and lab measurements should be taken to compare and adjust the value just in case. So that would be the equation that you'd use to get your coefficient of horizontal drainage. Whereas projects in category C, they should have more accurate estimated values for your horizontal drainage using any variation of method. So there's there's several methods that are out there that I won't go into detail here, but just keep in mind that category C projects, once again, projects with varving, projects with complex loading conditions, etc. They need to be they can't be designed for as conservatively as category A projects. And you'd use, this is just one example of a sort of equation that you'd use to calculate the value of horizontal drainage. So it takes a bit more effort. Okay, and now let's talk about, lastly but not least, is the drain influence zone. So main things or main principles to remember about the drain influence zone is that the drain influence zone is a function of drain spacing only. So that's the only thing that affects your drain influence zone. It's just how sort of far apart or close together your drains are spaced together. Vertical drains are commonly installed in square or triangular patterns. So square pattern layouts have greater ease in controlling the field. So essentially they're just easier to install just because there's less calculations or less effort involved when installing them. It's very straightforward. However, triangular patterns are preferred to provide more uniform consolidation between drains. So once again, if you're working in maybe a project where you really want to ensure that there's uniform consolidation, where you can't afford to be very conservative, or you can't afford to really be too conservative anyway in your calculations, and usually triangular patterns are used. So they take a little bit longer to do just because the way that they're sort of laid out, you have to be more careful when you actually install them. But once again, the main benefit of that is that they provide more uniform consolidation. So just because of the way that they're spaced out. So as you can see, when you have your sort of square pattern layouts, there's a certain amount of overlap that's done here, which is fine for projects that maybe in project category A, you can just get away with doing a square pattern and it won't really affect the consolidation between your drains. But if you go to the triangular pattern here, as you can see, there's less overlap, which accounts for more uniform consolidation between drains. So once again, it takes a little bit more effort to do triangular patterns, but if this is something that you really need to ensure, if you really want to make sure that you have uniform consolidation, then you would use a triangular pattern. And then as far as the drain influence zones are concerned, these are typically the functions that you would use to calculate that. So if you have your square pattern, you'd use this function, whereas if you have a triangular pattern, you'd use this function over here. So once again, this really, in order to really become acclimated with designing drainage patterns, you'd really just have to sort of practice it yourself. Also, another thing we'll talk about in the next section is you can also use numerical modeling program to do sort of a parametric analysis. In other words, you can compare and contrast different spacing functions and different patterns as well. So that's one way you could do it. So you could either do it like an actual sort of like a hand calculation, or you can do what's called a numerical modeling analysis, which I'll show you next, where you can sort of compare and contrast them via the program. So those are two sort of good ways to sort of learn how to do your drain influence zones. Okay, so now let's have a quick summary. So vertical drains are installed in clay soils to increase the rate of consolidation through increasing the rate of drainage. So the main function or the main purpose of vertical drains is, once again, like it says here, to increase the rate of consolidation by increasing the drainage. So before building your sort of structure on these large clay soils, it's always a good practice to drain them first. So that way, all the consolidation is taken care of, and then you won't have to worry about the soil consolidating once you actually have your structure built on there. Sand drains are created by drilling a series of vertical holes into a site with an auger and then filling the holes with sand. So as we discussed, sand has a very high permeability as opposed to clay. So once you have those sand drains installed, the water will, instead of having to seep vertically the entire way, will seep horizontally or laterally first into the sand drains and then very quickly vertically up the drains to the surface. And then prefabricated vertical drains, also known as PVDs or wick drains, consist of long strips of plastic, typically polypropylene, covered in geotextile fabric. PVDs are installed with excavators that use steel mandrels to protect the PVD during installation. PVDs are typically more economic and easier to install than sand drains. Overly dense or sensitive soils, as well as ground frost, are factors that can impede the installation of drains. So if you have soil that's too soft or too hard, that could cause problems. Or if you're installing them during a winter period, then if you have during periods of time when the temperature is below freezing or the freezing level, then the water won't drain. So like I said previously, drainage is usually done during the warmer months, so the water can drain without having to worry about freezing it. Valves are alternating layers of sediment and sedimentary rock that can make drainage more difficult. Category A projects have no soils that are low in sensitivity, they have no valves, and simple construction that require fewer drains and can be designed conservatively. So that's the main benefit of working in Category A projects, is that they're much easier to design for. And once again, the sort of properties that are involved is they have very low sensitivity, so they're very firm. You don't have to worry about them displacing, and they have no valves, so drainage is much easier. Category C projects have the opposite conditions. So once again, Category C project would have maybe soils that are very dense, very hard for seepage to occur in, that have lots of varving, which would affect the drainage, and then complex constructions. So these would require more drains, longer drains as well, and they need to be designed more carefully. Drains can be installed in square or triangular patterns. And then triangular spacing leads to more uniform consolidation between drains, while square spacing patterns are easier to install. So once again, each one has its advantage. Square spacing drains are very easy to install just because the geometry is very simple, whereas triangular spacing leads to more uniform consolidation. However, it takes a little bit longer. It's a little bit more complex to design for. Okay, so now we'll have the final quiz, and then afterwards we'll go over the numerical modeling example. So once again, it'll just be 3 multiple choice questions, and I'll make sure to give everyone a heads up once we reach our 4-minute mark. Okay, excellent. So I can see that everybody submitted their quiz ahead of time. Perfect. So what we'll do now is we'll go into just a quick demonstration or just a quick overview of how you can use a numerical modeling program to calculate your settlement and your consolidation. So what I'll do now is I'll pull up SoilWorks. And for those of you who are still aren't familiar with SoilWorks, what it is just our conventional geotechnical analysis software. And currently we're in the soft ground module, which specifically handles consolidation and settlement. So as far as the basic CAD commands, they're all the same. You can use these commands to create your geometry. You can also import your AutoCAD drawing just directly from your computer. So if you already have like a CAD drawing on file that you want to import, you can just do so using this function. But in any case, the main sort of difference, or the main thing that sort of sets the soft ground module apart from the other modules, are how it interprets or what sort of material models that it uses. So let's go to 1D ground material, or excuse me, 1D consolidation, as you can see this tab here. Let's go to ground material property. And as you can see, here are the properties that we have. So we have an embankment, which corresponds to this top layer here. This will be sort of our surcharge load. So it's like something that we're putting or a load that we're placing on our site to induce a consolidation. And then also we have a top clay and a bottom clay layer, as well as several layers of sand. So something that I'm sure you've noticed already is that when I go to my clay layers, under additional parameters, there's a whole other set of parameters that I need to sort of account for. And this is because I have the model type listed under clay. So let's take a look at some of these parameters. So naturally you have your unit weight, your saturated unit weight, etc., cohesion. Those are standard, and also horizontal and vertical permeability coefficients. But then if I go here, I have my SPTN values. I have C sub Z for calculation method. And then my compression index, once again, that's calculated from my odometer test. My expansion index, my pre-consolidation pressure, which you just input over consolidation ratio, secondary consolidated coefficient. And then also, very important to remember here, is the period for secondary consolidation. Here we have it listed as 20 years, and the end time for primary is 2.4 years. So there's a certain length of time that you're accounting for. Also your strength increase ratio, and then also logarithmic values for both bottom clay and top clay. So what you can do is you can have them listed here as a graph, but here I just have a single value for each of them. So as you can see, value. But if you need to, you can have also list them as graphs or functions. So once again, that's why getting your odometer test or performing those tests, or getting these values is so important. So even if you're using numerical modeling programs, you still need to make sure, you still need to understand what these values mean, and also how to calculate them. So that way, when you do have them, you'll be able to either plug them into those empirical formulas that I showed you earlier, or if you have something more detailed, or you want to have something more visual, you can have a numerical modeling program, and you can import them or input them directly into the parameter section here. So that's what makes clay sort of unique when it comes to design. Is you have to account for consolidation. You do so once again doing those odometer tests, and then you would get those values that I mentioned, and you'd have to input them here. Now, when you go to sand here, as you can see, it's much simpler. So you just have your unit weight, your saturated unit weight, your cohesion, and your SPTN value. That's because with sand you don't really need to worry about any sort of settlement or consolidation. All the settlement is just immediate when it comes to sand. So your primary focus really needs to be with getting these material properties correct. So anyway, once you have these material properties input into the program, what you need to do next is you need to design for any sort of drainage. So naturally, when you do your drainage, or when you're doing drainage design, you don't just have sort of one sort of scenario in mind. What you want to do is typically you have multiple drain types and multiple spacing types, and you want to compare and contrast to see which one works best for your project. And you would do so through these functions here. So first, you just need to define your drain property. So as you can see, here I have my various drain properties. So here I just have my rectangular spacing, but if I would like, I could change the array to a triangular arrangement as well. So that's something that the program can account for. So that's another advantage of just using numerical modeling programs. Instead of having to do this, sort of by hand or by spreadsheet, you can just very conveniently just select the drop-down menu, the option, and it'll take care of all the calculations for you. As far as the type of drains that you have, PDB, PBD, SCP, GCP, these all just represent different sort of drain types with different properties. So as you can see, I have three sort of drain types that I'm using here, all in rectangular spacing. And then here I just input my properties, my diameter, my permeability, etc. So here, as you can see, I have three different drain types that I want to model, and I want to compare and contrast them. My next step then would be to specify my strength increase zone. So your strength increase zone is simply the area that's being consolidated. So an important thing to remember, like I said previously, is that when clay consolidates and settles, it compacts and it becomes stronger over time. So what you want to do is you want to tell the program a specific sort of set of areas where the strength increases. So naturally it'll be this area over here will be your strength increase zone for these clays. So you'd select those. And then also another thing you would need to do is you'd need to calculate your settlement positions, or you just need to specify settlement positions. So with SoilWorks, as you can see here, actually let me turn these on here. So as you can see, these red lines each represent a certain position along the project site that I want to calculate the settlement for. So here, if I click on this option here, as you can see, everything's been predefined. And it's just a matter of defining your spacing, your increment, and the number of positions. So the reason I have different settlement positions to account for is just because the loading will be different in these spaces here. So these are all along sort of different heights of the embankment. So what we want to do is we want to see how the settlement differs under different loading. So naturally we'd expect the settlement to be maximum at this point over here, just because it's under the most loading. But we also want to see sort of the pattern it takes and how that loading affects the settlement directly. Okay. And then next, another thing you would need to do is determine drain spacing. So this is another very key advantage of using numerical model programs. So if I go to this option here, as you can see, I have my three drain types that I'm analyzing. If I go to PBD, and as you can see, the blue area, that strength increase zone, is highlighted. This is also the area where my drains are installed. So that's another important thing to remember. So instead of having to input your drains by ourselves through the program, what you can do is you can just specify a strength increase zone and then specify a spacing, and then the program will just automatically install or automatically simulate those drain spacings for you. So for example, here I have my PBD drain, and I have 1 meter, 1.3 meter, and 1.5 meter spacing. And what the program does is it'll take that strength increase zone and it'll simulate the spacing for each of those, each of these values here. And I can put as many drain spacing types as I'd like. So just imagine, if you have to do this by hand, you have to go through the same process over and over again, which can be very tedious and very sort of time-consuming. Because the calculations themselves are simple, but they take a long time, especially when you have multiple cases. Whereas if you're using a numerical modeling program, you can just input your drain spacings. You can just sort of list them, and when you run the analysis, the program will analyze all the different drain spacing scenarios for you just simultaneously. As you can see, I have three drain spacing types. So for my SCP, I have drain spacing of 2 meters, 2.2, and 2.5. And for my pack drain, I have 1.5, 1.8, and 2.2. So within, just by defining my spacing and my drain types, I've actually defined 9 different cases that the program will analyze for me. So once I take a look at all of my cases, I can find out the drain type as well as the drain spacing that best meets my needs. So here, and also keep in mind, there's no real limit to the number of drain spacing and drain types you can define. You can define as many as you need. And the program will analyze them all for you simultaneously. You can easily compare and contrast your results. So a couple other things to go over here. Preloading. As you can see, what you can do is you can input certain amounts of increments for your preloading. If you want to make it sort of like a stage loading where you incrementally add more load or increase the height of your surcharge load, you can do that as well. So just to keep it simple for this, just because it's a demo, I just didn't use this function. But if you're working in more complex projects where you have sort of stage loading, you would use this function. And once again, this is another function or another feature that can save you a considerable amount of time, especially for those more complex projects where you have multiple height increase or multiple increments. So instead of having to, sort of do it yourself or to do the calculations for yourself anyway for each one of these increases, you can just enter those heights, and the program will take care of each height increase, or excuse me, each case for you automatically. Okay, and then before I go into the results, I just want to show you the analysis cases. So as you can see, these are all the analysis cases I've created. So I have an undrained analysis just to sort of show how the site will consolidate without any drainage. And then I have 3 different drainage types, each of which has 3 different spacing options. Okay. And then when I go to my analysis results here, and the analysis itself only takes about a minute or 2, but just in the interest of time, I have everything completed. So this is what your results will look like. So here, if you go to the left, here you have your different scenarios. So first, let's take a look at our undrained analysis results. If I open this up here, as you can see, I have a set of results for each of my positions. So what I did is I selected, the middle section here, 81.29. Let's open it because this is the maximum or the critical sort of settlement area. What I can do is I can click on this, and if you look at the bottom of the screen here I have my settlement curve. So as you can see here, this red line represents my my settlement over time. So here's my time in days, and then this blue line here represents my load. So as you can see, the load is uniform just because I'm not increasing the height of the embankment or the surcharge by any. So this will be constant throughout the entire length of time. Whereas the settlement is, as you can see, it sort of settles slowly over time here. So first it drops down immediately. This is immediate settlement. And then we have the area of primary consolidation occurring. As you can see here, this curve sort of extends over a number of years. So for about I'd say about 3 to 4 years of primary consolidation is being predicted for this particular project. And also I can go here if I want to look at my graphical results. I can see my ground material properties, and I can see my primary consolidation. Also an immediate settlement for my sand. So this will be primary consolidation for my clay, immediate settlement for my sand, and this is my total sort of primary consolidation. So the program's saying about 1.5 meters of total consolidation and immediate settlement for this part of the project. And then secondary consolidation here, this is occurring, and as you can see, it's much less. So it's about, for this particular ground surface, it's about 0.0013 meters. If I go here, I have my consolidation curves, and then here I have a large spreadsheet that shows my total settlement, degree of consolidation, residual settlement, etc. for each of my surfaces here. So I have one for surface 17 through 7. And another thing I can do that's very convenient is I can sort of go back and forth between my various points here. So as naturally you'd expect less settlement to occur in this area just because there's less loading, which is what we see here. So everything's consistent with our expectations. And this one you expect it to be a little higher just because there's a little bit more loading. Now another thing that we want to do now is we want to compare to see how our drainage has affected the speed of our consolidation, just to see if it's really worth it to install those drains. So let's go back to our settlement curve. So as you can see, the primary consolidation occurs over several years. I think it's about 3 or 4 years total that this primary consolidation occurs. As you can see, it's very gradual. Now let's take a look at our drainage example here. So as you can see, now that we have our drainage example, and I know I went through a little fast, so here's our initial without undrained condition. Now if we go to our drain condition, as you can see, the curve is very different now. So as you can see, there's still that immediate settlement now, but now the time of primary consolidation has been reduced significantly. So as you can see, the settlement curve levels out right around the 200-day mark, as opposed to the 1,000-day mark, which is very, very important, which is very something that could really sort of change how fast a project can be constructed. So as you can see here, primary consolidation occurs around this time frame here. So for about 200 days, you can expect primary consolidation to occur, and then we're on to secondary consolidation. There's a very, very slight sort of change in settlement, or there's a very slight degree in the magnitude of settlement here, as opposed to primary consolidation. And then naturally you have your consolidation tables, if you want to get a better view. So the settlement is still the same. The difference is how fast that settlement occurs. And then also, if you want to see how it differs for your other sort of graphs, or excuse me, your other drains, so it's fairly similar. It's still about 200 days, or about maybe 250 now, a little bit closer. So as far as, sort of seeing how their drains differ, and this one you can see a very marked improvement. So this one definitely ends, primary consolidation anyway, definitely ends before 200 days. So this, from just what we see here, this particular drainage pattern and spacing would probably be the optimal one to use, because you'd want to get your primary consolidation to be done and over with as quickly as possible. So you can sort of see how primary consolidation differs for each of these graphs here. And then once again, another great thing you can do is you can go to result analysis, and this is just specifically to show how the software can help you extract your results or view your results. If you want to go over your different total settlement for different areas here, so each of these points represents one of the points along the length of the embankment. Naturally, total settlement occurs in the middle, and here you have your different analysis cases for undrained, as well as your 3 different drainage types. And the reason we only see 2 lines here is just because all of these overlap, all the drainage ones overlap. So that's something that you can do to get a better look at your results. And then one last thing that I want to show you before we wrap up is another cool feature of the program is that it actually allows you to create a report. So when you maybe get a set of results that's satisfactory, that meets your needs, instead of having to sort of take all of these results and individually sort of carry them over into a report, what you can do is you can just select the report generation icon, click perform analysis, and it'll actually extract all of your results into a Word document. So that way, you can save a lot of time in that respect and come up with a very you can very efficiently anyway come up with a very detailed and organized report. So as you can see, this is what their final report looks like. Your table of contents, so it has your initial conditions, your stability checks, and also it has your different drain examples as well. So if you want to show a particular client or maybe one of your colleagues that you went over several scenarios and that you got the results for those scenarios, you can do so through using this report. So as you can see, here are all of your preliminary data, as well as far as soil properties are concerned. Here are your input values, and then here's your drainage types, and also the proposed equations that you're using or the empirical formulas that you're using. So here's what you're considering for this particular project. And then here you have your information or preliminary information about smear zones, layout shapes, etc. So it's all listed here in a very organized format. And then you also have and these pictures can be enlarged as well. But you have pictures of your side or your project, your various spacings, the loads, etc., and backing heights. So all of your preliminary data is here. So now let's skip ahead to the and once again, these are for all the various cases that you're doing. And then also, if you skip down to the bottom here, you can have all of your results. So improvement period for check based on a specific date. So these are all things that can be altered. So you can go through here and you can see all of your conditions, all of your results, the duration, the settlement, residual settlement, etc., over a certain period of time. So this is something that's very unique about the programs. It has this really great feature that allows you, once again, to just focus on getting the results that you need instead of having to worry about sort of repetitive tasks like repeating calculations or generating a report. So this is something that a lot of our clients have used with satisfaction. We find that it really saves them a lot of time and a lot of legwork, and they're able to have more time to do other things because of this specific feature anyway. And as you can see, here are all your different drain types. So each one has its own sort of section with its results. So it's something that's very convenient, once again, especially if you have a large amount of information that you need organized. The program will take care of it for you. Okay. So, and once again, I know I've had a couple of people still express interest about learning more about the program. If you want to have a trial version of the program, or if you want to have me give you maybe a more detailed demonstration of what the program can do for you, just let me know, and we can set something up. But for now, and that was part 4, so that was what we went over about the result extraction and the constituent models. But next week, or excuse me, not next week, but 2 weeks from now, we'll conclude, we'll go into session 6, which will go over seepage design. So a lot of the principles that we went over here, just about sort of how water affects your project site, will be sort of carried over into this next lecture as well. So we'll go over coupled analysis for dams and embankments. So for those of you who work extensively in designing dams or levee or any sort of earth embankments, this is particularly useful, especially if you want to do a coupled analysis that takes into account how seepage or poor water pressure will affect the stability of slopes, or for those of you who are interested in rapid drawdown as well, as seeing how rainfall affects the stability of your project site. This is a particularly useful. This will be a particularly useful lecture or session. And once again, it'll take place on May 7th, 3 p.m. Eastern Standard Time, so that's 2 weeks from now. That will be a Wednesday. So thanks so much for your time and attention. I really appreciate it. If you have any questions or comments about today's lecture, if you have any suggestions on how to, for future reference, make these sessions better, I'm open to your suggestions. Feel free to contact me either by phone or by email. So thank you once again for your time. I really appreciate it. Hope you all have a good day, and I'll make sure to get the materials over to you by the end of the week. So you can expect an email with links to the recordings as well as links to the PDF files of these PowerPoints by the end of the week. All right, thanks again, guys, and I hope you have a good day.